L12 a table of moments of inertia. This table was produced by Professor Michael Richmond, School of Physics and Astronomy, Rochester Institute of Technology. It's nice to see all these in one table. Now we have done all of these except we haven't done the thick-walled cylinder. So let's do that, let's fix that. Then we'll have this table derived. So the entry we're interested in is a cylinder that has a thickness, so you have two R's, like an R1 and an R2. So like to have the big radius is R2, let's say here, like this. And this thing, comes down like this. And then this R here to go to the inner one. So this one's R1, the inner one, and then the R2 is the outer one. And we're going to go about the center. Let's go ahead and give this a length L and a mass M. And then what you do is you do this little ring around here. We're going to find an element and just go ahead and fill it in a little bit and see. So this go all the way down to the bottom here, and you can think of this as a little ring, a little shell, a little DV, a volume element. So you have here, this is going to be at a distance little r around, where little r is going to go from R1, the inner, to the R2, the outer. So this is going to be 2 pi r to get you your circumference, and that's going to be times L to get you your length, and a little thickness, dr. So we're all set here. So we have our 3 dimensions. We have 2 pi r going around times a little dr to get us a little thickness, and then multiply by L, so you have all of those little rings all the way going down to the bottom there. So the moment of inertia is going to be r squared dm, and remember dm is rho times dv, and the rho is going to be the total mass over the total volume. Now the total volume is going to be the pi r squared outer minus pi r squared inner, and that'll get us the area of the little strip, and then multiply by the length L. So here the rho has an m divided by pi, and then we'll pull out here the R2 squared minus the R1 squared times L. So this is the density. So therefore, our I is going to be obtained by integrating from R1, this is capital R1, to capital R2, and then we're going to have here this R squared, and then the dm, which is the rho, I'll just leave it as rho for now, times the dv, which is this thing, the 2 pi r L. So now we can pull out all the constants. 2 pi rho comes out, and that L comes out, and we go from R1 to R2, and we have an R squared and an R, so we have an R cubed. Integrate this, we get R to the 4th over 4 from R1 to R2. And this will give us 2 pi rho L from the beginning there. And then we'll have R2 to the 4th over 4 minus R1 to the 4th over 4. So now we can simplify a little bit. We can pull out the 4. So 2 over 4 is going to be 1/2 pi rho L. And then we have R2 to the 4th minus R1 to the 4th. Now we can replace for the rho, we can put the rho in, which is this big M over pi R2 squared minus R1 squared times L. And then we're going to have R2 to the 4th minus R1 to the 4th. But now watch this trick. 1/2, the pi's cancel, we have 1/2 M. And now here, we can write this as R2 squared plus R1 squared times R2 squared minus R1 squared. In other words, we're looking at this as an A squared minus B squared, where the A is R2 squared and the B is R1 squared. So if you square the A, you'll get then R2 to the 4th. If you square the B, you'll get R1 to the 4th. So doing that, then you're gonna have A plus B, which is R2 squared plus R1 squared, and then A minus B, which is the difference. And that's going to be over R2 squared minus R1 squared times L. And now you can see that these are going to go. And the L goes because we forgot to put an L. This L got dropped. So we want to put that L back in, and that L will go. So now we have the answer. We have the I is 1/2 M R, put the R1 first, R1 squared plus R2 squared. And let's go back to the table, and you can see that's what we have here. We have the 1/2 M and then R1 squared plus R2 squared. So we have derived the table of moments of inertia in this chapter. A lot of calculations.